In this goal, we are going to be talking about Dalton's law of partial pressure and also how to collect a gas over water. So a common way to gather a gas in the lab is to use water displacement. So just attaching a balloon to a test tube might not work because the balloon might melt as the test tube gets warmer. Also, the gas might escape if you don't have a good seal. And so a lot of times we'll use glassware and glass tubing, and we'll have a glass collection reservoir. And a lot of times this has measurements on it. And so we'll bubble the gas into the glass collection jar in this case, and then we can actually measure how much gas we end up getting. Dalton's law of partial pressure is this formula that the total pressure is equal to each of the individual partial pressures added up. So all the units must be the same for each pressure. So if you happen to have 4 different containers and you measure with 4 different pressure units, you would first have to convert them all to 1 unit, and then you can add them up. So here's a good example here. So I have 3 containers here that are all the same volume, and I can measure their pressures. So the first one is 200, then 500, then 400. Well, what would happen if I took all these 3 containers and put them into a 4th container that was also the same volume? Well, if you would do that, you would just add these up. And when you add them up, you get 1100 kilopascals is what your total pressure would be. So this is just saying you take the individual pressures, and when you add them all up, that will give you the total pressure. Now, when you bubble gas through your container, when you're finished, you're going to be able to measure your volume, but it also is very helpful with gases to know the pressure. And one easy way to figure out the pressure of a closed container is to put it into another container of water. And you want to have the water level inside the tube be equal to the water level outside. When you do that, then you know that the pressure pushing down, the atmospheric pressure, will be the same as the pressure inside the tube. So it's just an easy way to figure out pressure. Again, the pressure outside will be equal to the pressure inside as long as their water levels are the same. So in the lab, we're going to do this. You will gather your tube and gather your gas in your tube, and then you'll carry your gas collection tube over to a tall graduated cylinder, and then you will put it in that graduated cylinder and move the gas collection tube up and down until the water level inside is equal to the water level outside. And then all we do is we use a barometer to measure the outside pressure. So when we look at that gas that we collected over water, we will have the gas that we're interested in be there, but we will also have a little bit of vapor pressure in there. Well, how do I find the pressure of just the gas I'm interested in? Well, you have to go back to Dalton's law of partial pressure. So the total pressure will be equal to, again, the gas you're interested in. So I'll just say pressure A, and then also in this case, the water vapor pressure. So those added up together will give me my total pressure, which, as I said, a lot of times we just use the barometric pressure of the room because we measure the volume when the water level inside is equal to the water level outside. So this just becomes a math problem. If I want to know the pressure of just gas A, I would have to take and subtract the water vapor pressure from the total pressure. So I just rearrange that equation so I can find whatever gas I want. And this water vapor pressure, you're going to use a table to figure out what the pressure is. So a water pressure table should be in your packet. You'll use that same table on lab day when we do the lab, so you can look up whatever the water vapor pressure is according to the temperature of the room. Now on the AP test, you're going to get something like this. They probably won't give you a table. They'll just flat out tell you what the water vapor pressure is. So this is a clue that whenever they give you the water vapor pressure, that you have to subtract the water vapor pressure from the total pressure of the gas to get just the pressure of the gas we're interested in. So let's go ahead and look at this problem here. We have a 200 milliliter methane gas sample. And remember, a gas assumes the shape of its container. So this is going to be the volume of my gas. And let's see here, it's collected over water at, and there is my temperature. Remember, we got to change it to Kelvin. So 273 plus 22 is 295 Kelvin. And we have our total pressure is right here. And we have also our water pressure, which is right here. Okay, so what is the question here? Oh, what is the pressure of the dry methane gas? So I just take the pressure of my methane is going to be the total pressure minus the pressure of my water. And my total pressure is my 85.4, and I subtract my water vapor pressure, 2.6, and I get 82.8 kilopascals, and this is the pressure of just the methane. And a lot of times they'll ask, what is the pressure of the dry gas? So this is the dry gas, and it's dry because I mathematically subtracted the water vapor pressure away. So again, this methane will take whatever shape of the container it is, and if I were to mathematically take out the water vapor, I would still have that same volume of gas at that temperature. Here are some demonstration videos if you want to see how you collect a gas over water, but we are going to be collecting a gas over water in class, so it's kind of like you'll be doing your own demonstration. So let's look at this problem. We're looking at a decomposition equation here. So we have some potassium chlorate, and then we heat it up and we get potassium chloride, and we also get oxygen gas, and we're able to collect that oxygen gas. So it gives us some data here. So it tells us our temperature is 24 degrees Celsius. So convert that to Kelvin for when we do our gas law. So we get 297. And it says calculate the mass in grams of oxygen that's obtained. So we have the pressure of the water, and why did they give that to us? That's because we need to remember to subtract the water vapor pressure away from the total pressure. And they already have it in the same unit. So the pressure of my oxygen, again, I'll take the total pressure minus the water vapor pressure, and my total pressure, 762, subtract 22.4. So if you're ever wondering, well, why did they give me water vapor pressure? That's because you've got to use it. So there won't be a table like in your homework. They'll just flat out tell you what it is. Okay, this is millimeters of mercury. I like using atmosphere, so I'm just going to divide by 760 millimeters of mercury, and that will give me my atmospheric units for our next step. So this is almost 1 atmosphere. All right, so we want to find out the mass. So which equation should we use for PivNert? So we can use the MVP Mr. T arrangement of PivNert, and we are going to solve for that M because that's going to be our grams. So we need to take pressure, which we just found. Now this is the pressure of just the gas, so it needs to be the dry gas pressure, and times the volume, and this one is in milliliters. Now remember, R is 0.08 and it is in liters, so that is why you always want to write your units out. How do I go from milliliters to liters? You're going to move your decimal over 3. And so I'm going to end up having 0.128 liters. So watch out for that. Okay. And then I'm going to multiply it by the molar mass of oxygen. And the molar mass of oxygen, remember it's O2. So it's going to be 16 plus 16, 32 grams per mole. So I think I can scrunch it in here, 32 grams per mole. All right. So that's on top, and on the bottom is my ideal gas law constant. And my temperature, we already converted it into Kelvin. And now we can just do the math here. And I end up with 0.164 grams of oxygen is my mass. So again, using Dalton's law of partial pressure, and then using the molar mass, which we looked up from the periodic table, and then using Pivnert, that's rearranged with the molar mass, so the MVP Mr. T formula, and we get how many grams of oxygen. The AP board loves these kind of questions because there are multiple steps. So they'll give you a point for the first step, a point for the second step, a point for the third step, and on the fourth step, they might ask you to explain stuff. So this is what the AP written exam is exactly like. So that's why we're doing lots of problems that have a lot of things in them. Because each gas in a mixture acts as if it is alone, we can relate the amount in a mixture to partial pressures. So here we're using Pivnert, and we're looking at the moles of just one of the gases in a mixture to the total moles, and we end up getting what's called the mole fraction, and that's given an X, and this is found on your formula sheet. You just have to know how to use it. So when you look at the mole fraction, you look at the moles of one thing and you divide it by the total moles, and they give it this letter X. Okay. To find the partial pressure of just one gas, you take that mole fraction of the one gas and multiply it by the total pressure. So you're basically taking the mole ratio, or the mole fraction is what it's called, and multiplying it by the total pressure. And then this will give you the partial pressure of your gas. So let's do a sample. So we have a sample of natural gas, so that is methane gas, CH4, contains 8.24 moles, and we have 0.421 moles of, that is ethane gas. And we also have 0.116 moles of a propane gas. And then it says if the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of the propane? So we need to find the total pressure. So we need to find the total amount of moles and then find that mole fraction. And we already know the total pressure. So really all we need to know is what this X is. So I need to take the moles of just my methane, so the one that I'm interested in, and I'm going to divide it by the total. So the total, you're going to take the methane plus that ethane plus that propane. And when we do this, we get 8.24 over our total, which is 8.777, and we have our fraction as 0.0132. So we're going to put that into this equation that we have up here at the beginning. So we have our mole fraction, again, just the gas we're looking for, and it's just a number. So there's no units because it's moles divided by moles. And I multiply it by the total pressure, which is the 1.37 atmospheres. And I get my total partial pressure, my partial pressure of 0.0181 atmospheres. And I have 3 sig figs, so I'm good. So this chart is showing what happens with the pressure as the temperature goes up. So as you increase the temperature, then your pressure will increase. And this is what happens with water. So if you have if you collect a gas over water and it's quite cold, you're not going to get very much water vapor pressure. But if your water is very, very warm, you're going to get more water vapor in that total pressure. So that's just a relationship that as the temperature goes up, the water vapor pressure goes up. The reason this is as those water molecules jostle around in the liquid, because the temperature is causing them to move faster, their collisions will be more violent and you'll get more water vapor appear above the water. So it basically the water jumps out and becomes a vapor because of the violent collisions.